Today, we're going to pull back the curtain on something you use every single day, but probably never think about. The secret rules that stop our digital world from completely falling apart. Let's get into it. I mean, seriously, have you ever really thought about this? You're sending money, your banking app crashes, total panic, right? But then you restart it and poof, the money's either where it's supposed to be or it's safely back in your account. How on earth does that actually work? Well, I can tell you it's definitely not magic. The thing is, behind the scenes, modern databases are, well, they're pure chaos. You've got thousands, sometimes millions of people, all trying to do things at the exact same millisecond. Imagine everyone trying to grab the last concert ticket at once. Without some really smart, really strict rules, it would just be a total disaster. We're talking corrupted data, huge errors. The whole system would just collapse. So how do we tame that chaos? How do we keep everything in order? Well, the answer comes from this one simple idea that is just incredibly powerful. It's time to meet the hero of our story, the transaction. So what is a transaction? The best way to think about it is like a sealed package. Inside that package, you might have one instruction or a whole list of them. But here's the key. The database makes a promise to treat that entire package as one single, indivisible thing. It can't be broken apart. And the absolute classic example, the one everyone uses, is a bank transfer. Because when you think about it, it's not just one action, is it? It's really two. Step one, the system has to take the money out of your account. Step two, it has to put that same money into the other person's account. A transaction is what wraps those two distinct steps into that single sealed package we just talked about. And this right here leads us to the golden rule. It is the most important thing to understand about transactions. That whole package of operations, the withdrawal and the deposit, they either both succeed or they both fail. If any part messes up, say the deposit fails because the network drops, the whole thing gets canceled. The withdrawal is just undone. Poof, like it never even happened. It is all or it is nothing. Okay, so what gives transactions this superpower? Well, they live by a very strict code of conduct. It's a set of 4 rules, and you'll hear engineers talk about it all the time. It's known by the acronym ACID. And these 4 properties, they are the absolute bedrock of what keeps our data safe. All right, first up, A is for atomicity. And this is literally just a fancy word for that all or nothing rule we were just hammering on. It means the transaction is treated as a single, indivisible unit, like an atom. You can't split it. So for a bank transfer, it means it either happens completely or it's totally rolled back. You can never, ever have that nightmare scenario where the money is gone from your account but hasn't shown up in the other one. Okay, next up is C for consistency. This one's all about playing by the rules. The database has rules, right? Things like an account balance can never go below 0. Consistency just guarantees that a transaction will never break any of those rules. If you try to withdraw more money than you have, the transaction will just fail. It makes sure the database goes from one correct state to another correct state without ever entering some weird invalid territory. Then we've got I for isolation. Now this one is huge in our chaotic multi-user world. Isolation is what makes sure that 2 transactions happening at the same time don't mess each other up. In a perfect world, your transaction would be in its own little bubble, completely unaware that anything else is happening in the database. But, and this is a big but, creating that perfect isolated bubble, that slows things down. And that trade-off is going to become really important in just a minute. And finally, D for durability. This is the database's pinky swear. It's a promise that once it says a transaction is done, or committed in database speak, that change is permanent. It's written in stone. It's saved somewhere that will survive a power outage, a server crash, you name it. A lot of systems do this using something called write-ahead log, basically writing down what they're about to do before they actually do it, just in case. So, living by the ACID code sounds great, but it's not always simple. That I for isolation we talked about, it's constantly under attack from some pretty nasty characters. These are what we call concurrency problems. So let's meet the villains of our story, the things that try to mess everything up when transactions start bumping into each other. First villain on our list, the dirty read. Okay, picture this. Transaction B is in the middle of updating some data, but it hasn't saved, it hasn't committed yet. Then transaction A comes along and reads that in progress, temporary, dirty data. The real problem happens if transaction B fails and has to roll back its changes. Suddenly, transaction A is working with information that, poof, never even existed. It's making decisions based on a ghost. All right, next up, the non-repeatable read. This is when the ground shifts right under your feet. Imagine your transaction reads a product price, say it's $50. Then it goes off to do some other work. But while it's away, another transaction swoops in, changes that price to $60 and commits. Now your first transaction comes back to read the price again, and suddenly it's different. The data you read the first time isn't repeatable, and that can cause all sorts of chaos in your calculations. And believe me, the list of bad guys goes on. You've got phantom reads, where you run a search, and then you run the exact same search a second later, and suddenly new phantom items have appeared out of nowhere. Or the one we've probably all experienced, the dreaded lost update. That's when two people edit the same document, and the last person to hit save just completely wipes out the first person's changes. So frustrating. So, how do we fight back against these data villains? Well, this is where it gets interesting. There's no single magic shield. Instead, it's more like choosing your level of armor. It's a strategic choice, and these defense levels are called isolation levels. And here is the fundamental trade-off, the one that every database designer has to wrestle with. It's a constant battle between perfect, bulletproof safety and raw maximum speed. You see, to guarantee that transactions are perfectly isolated from each other, you have to do a lot of locking things down, making other operations wait in line. And all that waiting, well, it just slows everything down. This table lays it all out beautifully. These are the standard isolation levels you'll find in most SQL databases. Look at the top. You have Serializable. That's Fort Knox. It prevents every single one of those problems we just talked about. But it's also the slowest because it basically forces transactions to form a single file line. Then you go all the way to the bottom, read Uncommitted. It's blazing fast for sure. The trade-off? It offers zero protection. It's the Wild West. So here's the really fascinating part. Where do most real-world systems actually land on this spectrum? Well, most of them don't pick the extremes. They pick a compromise, a sweet spot right in the middle. The read committed level is the default for a ton of major databases you've heard of. It protects you from the absolute worst villain, that dirty read, while still giving you pretty good performance. It's the practical, real-world choice between being perfectly safe and being super fast. So, when you put it all together, all the rules, the trade-offs, the villains, what's at the center of it all? It's the transaction. Just this one simple idea, a single unit of work that follows its strict ACID code, fighting off data corruption in the background every single second of every day, keeping everything we do online safe and sound. And that really leaves us with a bigger question, doesn't it? This whole idea of isolation levels proves that even in the very logical world of computer science, there are no perfect answers. It's always a trade-off. And as we all demand faster apps, faster websites, instant everything, it makes you wonder, how much safety are we as users and as builders actually willing to trade for just a little more speed?